Well, we're going to take a look at complex numbers. And complex numbers, they're a different kind of number from what we're used to. But where they come from, the answer is a question that, well, maybe you've encountered this in a calculator. But let's say you want to compute the square root of -1. Now, usually you put this in a calculator, it says there's an error. But what we've decided to do in mathematics is we've decided to give this a value. Value of sorts. We'll call this I. Now this might seem kind of strange, especially if you take like a handheld calculator, you put in square root of -1, it gives you an error. Like, why are we doing this? Well, it turns out the ability to do this lets us do all kinds of neat things with studying waves. That's probably quantum mechanics uses this sort of thing. It's actually very helpful in science. So it also allows us, for better or worse, well, worse, but it allows us to solve a quadratic equation such as this. And if you try to solve this using your quadratic formula, you're going to end up taking the square root of a negative number. This allows us to do that. So if we just accept this, if we say, okay, this is good enough, then we end up getting this sort of other form of number system that we call the complex numbers. And the complex numbers work like this. A complex number is of this form. So if you recall real numbers, what are real numbers? Well, those are all the numbers that we usually deal with. Numbers you count on your fingers, 1, 2, 3, 4, 5, 0, negative numbers, those are also real numbers. Fractions, like 1/2, -2/3. And then what are called irrational numbers, numbers like pi or the square root of 2. They're numbers that you can't represent as a fraction. Well, all these together are real numbers. So now we're getting something even beyond that, and that's the complex numbers. And what we do for complex numbers is we take a couple real numbers, and then we attach an I to one of them, adding them together. So for example, a complex number, we could take a real number like 5 plus 2 times I. That's a complex number. And we could take something like 1 plus pi I. We can do something like that. And again, this is an irrational number, but irrationals are still real numbers. But this entire thing is called a complex number. Now, numbers, real numbers that we're familiar with, we graph those on the real number line. We've seen this before. So this could be 1, 2, 3, and so on. Pi, it's on the real number line. It's somewhere out there, right around there. And let's see, -1, -2, -3. So right here would be -2 1/2. And then negative e. E is kind of like pi. It's 2.71 and a string of numbers after that, 2.71 that goes on forever and ever. And again, you can't represent it as a fraction. So real number line, positive numbers, negative numbers, 0, fractions, irrational numbers, they're all part of the real number line. So we're used to graphing real numbers here. What about complex numbers? How do we graph those? Well, what we do is we end up graphing them two-dimensionally. So to graph a complex number, we don't graph it just on that real number line. This right here is our familiar real number line. So this is what we might call the real axis. And then this vertical one, we call the imaginary axis. And the reason we do that is complex numbers, or this idea that square root of -1, instead of calling it an error like we do on the calculator, we're now going to call it I. This was referred to once as an imaginary number, and I think the term was sort of derogatory, like doing this is kind of silly. But again, it's turned out, it's worked out in engineering with waves, it's worked out with science, say with quantum mechanics. Doing this actually helps out really well. So if we're going to graph, say, 2 plus 3i, well, that's going to be here. 2 above the 2 on the real axis, and then here's 3i on the imaginary axis. And so that's how we would graph that number. And if we took a look at, say, this one here, this point, and we call this the complex plane. This is where we graph all of our complex numbers. They have the imaginary part and the real part. Well, the real part is -2. And you could say plus -2i. You could do that. But we'd probably just write it like this. -2 minus 2i. And so that's how we picture complex numbers. We have to do it using 2 dimensions, a real dimension and an imaginary dimension. So that's sort of an introduction to what these things are. And again, they're helpful for studying waves, they're helpful for studying quantum mechanics. So let's start out with just our friend I. So because of its usefulness, we're going to study I. What if we take powers of I? Well, let's say we have I squared. Well, this is the square root of -1 squared. And what that's going to do is just give us -1. All right. What about I cubed? Well, we can rewrite this. Square root of -1 squared times another square root of -1. But we know what this is. That's going to be just -1. And, okay, -1. But this is, again, square root of -1 is just I. So this will be -1 times I, or -I. I to the 4th. Well, we can write this as I squared times I squared. Now, I squared, we know is -1. So -1 times -1 is +1. So this is what we have so far. I square root of -1. I squared is -1. I cubed is -I. I to the 4th is +1. I to the 5th. Well, we could say this is I to the 4th times I, or 1 times I, which is just I, or the square root of -1. So what's happening here? I, square root of -1. -1, negative I, 1, but then I to the 5th, we're back to the square root of -1. I to the 6th, if you calculate that, will give you -1. I to the 7th will give you negative I to the 8th will give you 1, and I to the 9th, if you work it out on paper, it gives you the square root of -1 again. So as we increase the powers on I, we just cycle through these results. So what's going to happen is we can take a look at higher powers of I and rewrite them, compute them, using this knowledge of these beginning powers. Let me show you. So let's say we want to compute I to the 37. Well, what we can do, think about our multiplication. What's the largest number that's smaller than 37 that's a multiple of 4? A number that's less than 37 that's a multiple of 4, but it's closest to 37. So like 12. 12 is a multiple of 4. It's 4 times 3. But it's not the largest number that's less than 37 that's still a multiple of 4. Like 24 is also a multiple of 4. 6 times 4. And it's bigger than 12. The number we're looking for here, the largest such number that's a multiple of 4 but still less than 37, 36. So we rewrite this as 36 plus 1. Well, let me show you what I'm going to do with this. Because 36 is a multiple of 4, it's 4 times 9. Now I'm going to break this up. It might have been a while, but recall that when you have the same base, it's a rule with exponents. When the bases are the same, you add the exponents. Or if you have a base that's adding exponents, we can do this backwards, rewrite it as a product. And so that is what I'm doing here. Now there's another rule that goes like this. If you have an exponential expression and you give that a power, you multiply the exponents. Or you can go backwards. You can start with this and go to here. And that's what we're going to do with this. The reason why I'm interested in I to the 4 is always going to be 1. So this will be 1 to the 9th power, which is just 1. It gets rid of all these i's. Finally, 1 times I is just I. And that's going to be our answer. Now, there's a trick, there's a shortcut we can do here. And this is how it works. So if you're thinking, I don't know if I can break numbers into that, let me show you where the shortcut helps. You might say that, well, the largest number less than 37, it's a multiple of 4. Okay, I might be able to figure out that's 36. But what if we have something like this? How do you figure this out? Well, let's go back to that one that we did, I to the 37. There's a trick you can use. It's take this, divide it by 4. And we're going to use long division. What we're interested in is the remainder. So 4 goes into 37. At most, 9 times. 9 times 4 is 36. Subtract is 1. And there's the remainder. So the way this trick works, this will always be equal to I, where the power is the remainder. And sure enough, excuse me, we get our I. So this is just kind of a trick. It's kind of a shortcut, if you will. So if we take the power, always divide it by 4. Always 4. And then you do the long division, and then whatever the remainder is, that is going to be the exponent for your I at the very end. And it just turns out to be I. Is what we got last time. So let's take a look at this. We divide this by 4. You're always dividing by 4. 4 goes into 25 at most 6 times. 6 times 4 is 24. Subtract is 1. Bring down to 3. 4 goes into 13 at most 3 times. 3 times 4 is 12. Subtract is 1. There's no more numbers to bring down. We're not going to try to do anything with decimals. So this is the remainder. So according to our trick, I to the 253 is equal to I to the 1, which is just I. And so this is going to be our answer. Let me do another one. Let's say you want to figure out this. Well, again, we divide it by 4. 4 goes in the 4 at most 1 time. 1 times 4 is 4. Subtract 0. Bring down the 8. 4 goes into 8 2 times. 2 times 4 is 8. Subtract 0. Bring down the 2. 4 goes into 2 0 times. 0 times 4 is 0. Subtract is 2. Bring down the 1. 4 goes into 21 at most 5 times. It's 20. Subtract is 1. So, and this is purely coincidence. You don't always get a remainder of 1. What you'll get I to the 4,821 is equal to I to the 1, or just I. We do one more. I to the 102. Again, always divide by 4. 4 goes into 10 2 times. 2 times 4 is 8. Subtract is 2. Bring down the 2. Or I should say at most 2 times. 4 goes into 22 at most 5 times. 5 times 4 is 20. Subtract is 2. So now the remainder is 2. So that means I to the 102 is equal to I to the 2. And what's I squared? Negative 1. And that's our answer. All right. So first off, we're going to look at adding and subtracting these things. So let's say we have this. So how do we add these things? Well, what we're going to do is gather like terms. We're going to combine the real parts. We'll combine the imaginary parts. So that means this will be 7 plus 1 plus 2i minus 4i. Or 2i plus negative 4i. So this will be 8 plus negative 2i or 8 minus 2i. And that's it. So we're just combining like terms. Now what if we're subtracting? Well, now we got a minus sign to deal with. And we had better distribute that minus sign to begin with. So in this case, we need to distribute this minus sign first. And then minus to the 14 is minus 14, but minus to the minus is plus 9i. Now we combine like terms. We combine the I terms, that's going to give us 8i plus 9i, 17i. And then we have the real term out here just by itself. And so that's going to be our answer. All right. So next we're going to look at multiplication. And the thing with multiplying two complex numbers is we're going to end up doing FOIL. So if you remember what FOIL is, we multiply the first terms of our binomial, of each binomial, the outer terms of the entire multiplication, the inner terms of the entire multiplication, and the last terms of each binomial. So the first terms of each binomial, the outer terms of the multiplication, the inner terms of the multiplication, last terms of the binomials. So what this gives us, negative 15. Negative 5 times I is minus 5i. 4i times 3, 12i. And then 4i squared. When we multiply an I term in a real number, it's like multiplying 4x times 3, you'd get 12x. 4i times 3 will give you 12i. And then adding a negative, that's the same as subtraction, or subtraction is the same as adding a negative. This is the one we got to deal with, though. Now we can combine some like terms. Negative 5i plus 12i, that's going to be 7i. But then this plus 4i squared, remember, I squared is negative 1. So that means that's really 4 times negative 1. And then combine these like terms, negative 19 plus 7i. So that's the main idea with multiplying complex numbers. I'll do one more. Now, this one's sort of interesting. They put the I term in front of the real term, and you can do that. That's all right. If you're going to write this in a more proper approach, you would say this is really another way of writing -5 plus 7i. These two expressions are the same thing. So just so there isn't any confusion. Now to do this, we want to distribute that -3i. This is what we call a purely imaginary number. It's purely imaginary because there's no real part to it. Like this is a real part to this complex number. That's the imaginary part. So we'll distribute this -3i. -3 times 7 is -21. 1, there's 2 i's, that's I squared. And then -3 times -5 is plus 15, and this brings over an I. So we get something like that. But remember, I squared is -1. Negative and negative is positive. And there we go. There are no more real terms or imaginary terms to combine. All the powers of I have been, well, we've converted them. So there we go, 21 plus 15i. So division. The thing with division, we gotta be a little careful with this one. So what we're doing here, we're taking the purely real number 2 and dividing it by the complex number 3 minus 1. Now the way we do this is we try to eliminate the I in this denominator. So we're going to rewrite this as a fraction and then eliminate I in the denominator. So that's going to be our goal. Now, how do we do that? Well, what we're going to do, we're going to multiply what's called the complex conjugate. I want to multiply top and bottom by the complex conjugate. Now, what is that? Well, it's expressed by writing a bar, and this isn't a fraction bar, it's just a bar on top. This means complex conjugate. What that's equal to is just this. If there's an imaginary part to that number, the sign on the imaginary part changes, but the real part doesn't change. So if we have 2i, the complex conjugate of 2i is -2i. And that's it. So what are we going to do with this? Well, this is what we're going to do. We're going to multiply top and bottom by the complex conjugate of 3 minus I. Now, again, you might be saying, well, is this changing anything? Well, keep in mind, you can say that we're really multiplying this to this fraction. But yeah, is that changing anything? Well, it's going to change how things look, but a number divided by itself is always equal to 1. So technically, all we're doing, this entire thing is just the number 1. So we're just multiplying this thing by 1, and That doesn't change it. So it's really staying the same. This is just going to be a trick to make it look a little different. And it lets us actually compute the division, or compute it where there isn't an I in the bottom. So all right, so here we go. The way we do this, multiply top and bottom by the complex conjugate. So we just distribute the two. This one we're going to FOIL. 3 times 3 is 9. 3 times I is 3i. And this is where the complex conjugate's coming in. It's helping us. We have a positive 3i. Negative I times 3 is negative 3i. Those I terms are going to cancel. Negative I plus I, looks like they're not going to totally go away. Negative I squared. So at least the middle part, that's going away. Those are canceling. But keep in mind, I squared, that's actually -1, which is a plain real number. So negative minus a negative is a positive. And so we're going to divide each of these by 10. Now I just want to review something. Keep in mind that a plus b over c is a over c plus b over c. And it's same if it was minus. So this was a minus b, you'd have a over c minus b over c. So 6/10 plus 2/10 I. And then we reduce this 3/5 plus 1/5 I. And that's it. Let me do one more. Again, what we're going to do, we'll multiply the top and bottom by the complex conjugate of that denominator. So the complex conjugate of 2 plus I, 2 minus I. Again, we just changed the sign that's on the imaginary part. We leave the real number, the real part, alone. So this will give us again, we're just multiplying by 1, but we can rewrite 1 as 2 minus I over 2 minus I. Again, this is just equal to 1. A number divided by itself is 1, except for 0. 0 divided by 0 is undefined. But all the other numbers, complex numbers included, the number divided by itself is just equal to 1. So again, we're going to FOIL. First times first, 4. Outer, minus 2i. Inner, 6i. And last, minus 3i squared. Now let's take a look at the bottom. 4 minus 2i plus 2i, seeing that cancellation, minus I squared, which is really just negative 1. Keep a note there, those are canceling. Negative 2i plus positive 2i, those cancel. So let's see, for minus 2i plus 6i is positive 4i, minus 3. Now I squared is minus 1. Then we have 4 minus, again, I squared is minus 1. So we've got that. 4 plus 4i, negative and negative is positive. Negative and negative is positive. So now we can simplify. Add these real parts together. That adds up to 5. And then finally, we divide 5 into each of the top numbers. And that's going to be our answer. All right. So something to be aware of, and you mentioned this in the text, you might recall the square roots. Square root of a times b is the square root of a times the square root of b. And this is true of all other roots. Now, where you want to be careful here is when we're dealing with negative numbers. If this is negative, this works backwards. If you have a square root of a times the square root of b, it's equal to the square root of a times b. So for example, the square root of 2 times the square root of 3 is the square root of 2 times 3, or the square root of 6. Now with negative numbers in the square roots, we got to be careful. So let me show you something how this usually goes. Square root of negative 2, square root of negative 3. What they want us to do is recognize this is an imaginary number. So is this one. So this is really the square root of negative 1 times 2, square root of negative 1 times 3. And so we break up the square roots like this. Again, these are just I. So get I square root 2 times I square root 3. We multiply the i's together. We get I squared square root 2 square root 3. I squared is negative 1. So negative 1 square root 2 square root 3. Or negative 1 square root 2 times 3. Again, we can combine the square root 2 and square root 3. So we get negative 1 square root 6 or negative square root 6. And so this is actually our answer. Now I'm going to do this a little quicker. Let's do a shortcut here. What this basically says is this. When we take the square root of a negative number, we want to make sure we pull an I out. So square root negative 2, square root negative 3. I square root 2 times I square root 3. This is the big shortcut. So you can basically go from here to here if you want. And this will give us I squared square root 2 square root 3. We know I squared is -1. Square root 2, square root 3 is square root 6. And so we get our answer. It probably still seems like quite a bit. You might be asking, well, is there a shorter way? And some of you are probably seeing this. And let me show you. This is something you want to watch out for. Some of you might be thinking, well, wait a minute. Why don't we just combine the square roots right now? Why go through all that stuff? Well, what happens is you'll get square root -2 times -3. Negative and negative would be a positive. And so your answer comes out square root 6, not square root -6. The reason this is important, the square root of a negative number should have an I. This is an I number. This is also an I number. And when we multiply I numbers, the answer comes out negative. Like I times I is -1. Square root 2i, square root 3i should be negative square root 6. But if we combine the square roots this way, we're ignoring and we're erasing the existence of these being actually I numbers, imaginary numbers. And so we end up getting a positive answer. But when you multiply two I numbers together, two purely imaginary numbers, like these, your answer should be negative, not positive. So when we do these square roots, we want to be careful that we don't combine them right away. What we really want to do is convert them so they're clearly I numbers. And when we pull an I out, we can drop the negative. And then we can combine. So if you have a negative in the square root, you can, in a sense, factor it out as an I. Now these are correct. These are I numbers, and so we'll get I squared. You can now combine the square roots of square root 6, or negative square root 6. This is the right way to do this. This is not the right way to do this. So we don't want to accidentally remove the I nature of these numbers, which we can accidentally do by combining them too soon. All right. So let me do an example of that. So the first thing I'm going to do, I'm going to factor out the negative sign. So this disappears, or it factors out rather, as an I. Now this is a positive number, so there's no I to factor out, or no negative sign to factor out into an I. So the negative came out to an I, the negative came out to an I. So this negative became an I, this negative became an I. So now we distribute. The I in the square root 8 will be distributed. So when these two multiply, we'll get I squared, square root 8, square root 3. When these are combined, we get minus I square root 8, square root 5. And now when we have positive numbers in the square roots, now it's okay to combine them. I squared, square root 24, minus, oh, it's I squared, I square root 40. And then I squared is -1. or negative square root 24 minus I square root 40. So mathematically, this is what you want. Now we want to simplify this a little bit. Simplify it a little bit, clean it up. But if you get to here, you're on the right track. Now to simplify this, we want to remember how to simplify square roots. And again, we're using that rule. Square root AB is square root A times square root B. Look at square root 24. Well, that's the square root of 4 times 6. So we can break this up like this. Square root 4 times square root 6. Now what's the square root of 4? That's 2. 2 square root 6. And square root 6 doesn't have a clean square root or a perfect square root. So we'll just reduce square root 24 into something like that. There we go. Square root 40. Well, 40 is 4 times 10. I'm looking for those perfect square numbers. I'm trying to break these down into a product of perfect squares. If I can't, or product with a perfect square. And if I can't do that, I'm just going to leave it like this. If like this was square root of 21, well, 21 is 3 times 7. 3 is not a perfect square. 7 is not a perfect square. So I'm just going to leave it as square root 21. But square root 40, I can rewrite as a perfect square times 10. So this is going to be square root 24. This is square root 40. So now, I'm going to rewrite my answer as square root 24 minus I 2 square root 10. And let me see how they're combining that. Let me double check that real quick. They'll put the I in front. That's what they'll do here. And that's going to be our answer. So that's going to be it for complex numbers. If you have any questions, let me know.